Now, let's talk about normal stress. Suppose we have a rod, and this rod has a force P that is exerted on both sides. Now, these forces have to be equal so that our member is in equilibrium. Now, if I look at a side profile of my rod, I will have force P and I will have force P acting on both sides. Because these forces are acting on the same axis, we call these forces uniaxial forces. Uniaxial forces because they act on the same axis. Now, what is going to happen is that these two forces are going to act opposite to each other, trying to pull on this member. And the more you exert this force on this member, the more it will start to stretch because of these two forces that are acting on it. Now, suppose maybe it is a concrete member or a steel member and it's being pulled. Now, in essence, you're supposed to see some stretching, but inside our member here, there are going to be some internal forces that are going to try and oppose that motion of stretching. Now, as the P acts on the member, these internal forces are going to resist the effect of the force that is trying to stretch our member. Even if my member was experiencing compressive forces and you found out that these forces were pushing against the member, instead of shrinking into a smaller size, there would be the same type of internal forces that are acting to resist that compression. To expose these internal forces that are acting inside here, that are resisting the effect of the external forces, we are going to cut our section open here, and it's called a method of sections. Now, I'm going to cut my member here. I could cut it at anywhere as long as I expose the internal forces that are resisting the effect of the external forces. Now, I cut it here. Let's take the one at the top. What I will have now, I will only have a portion of my member with the force P acting on my member. However, inside here, I will be exposing all these internal forces that are resisting the external force. Now, you will notice that they will act in the opposite direction because they act in the way that my member here remains in equilibrium. Now, we do not lose the balance of forces here. These internal forces will be enough to balance the force of the external force. Now, even if I took this right side of my member, I will have a portion of my member with a force P acting in this direction, and inside I will have the internal forces that are resisting the effect of the external force. I could represent these forces in any way that I like. I could write a resultant of all these forces as just one line instead of all these lines. Or I could make even more of these lines, but that are smaller, that will be equivalent to bigger green forces. Now, the thing that happens is that you just have to understand that these forces are acting on the area. Whether I draw a resultant, you just have to remember that these forces are distributed across the sectional area of my member. Anywhere on the area of this member, there is a little portion of my force that is acting on that member. So we said they are distributed over the section area that is given by A. What we focus on instead is to look at the stress on that cross-sectional area. Now, what we call stress, we are basically talking about the intensity of this force on this area. Now, the more force you will have, the more intense the effect will be on this area. So this stress, it describes the distribution of internal forces within a body. So the stress gives me the intensity of a force that is acting over a section area A. Now, to calculate that stress, to find that intensity, we take the force that is being exerted on the member, which will be equal to the internal forces that will result inside here, and we divide that by the cross-sectional area. So if you have a rod like this, your area will be pi r squared. If you have a square member with a cross-sectional area of a square, it will be L times B. It's just important for you to know that stress represents the intensity of the force that will be felt internally here, as these forces try to balance with the external forces. So our forces is given by newtons, and our area will be given by meters squared. Therefore, our SI units will be newtons per meter squared. In SI unit, this is also called a Pascal. Now, if your measurements are given in millimeters, then newtons per millimeter will be mega pascals. But for people who are using the US units, then they will use pound over inch squared, a pound square inch. Now, so far with our rod here, the force that are acting on the rod have been perpendicular to the surface of the rod. Now, if I have P here and I have some resultant forces inside here, they've been acting perpendicular to the surface. So if you have your surface here, your forces will be perpendicular at a 90 degrees to the surface. Now, if a force is perpendicular to the surface, that force is called a normal force. Now, if you have a normal force and you want to find the intensity of that force, which is stress, you are then looking at normal stress. Normal stress gives you the intensity. It describes the distribution of internal forces that are acting perpendicular to your surface. Now, normal force is presented by a symbol sigma, and we said that stress is force over area, so we will want to find the normal force that is acting here, which is N over the area A. Now, this is the formula that you find for normal stress. Remember that the normal force acting perpendicular will just be equal to the external force that is being experienced on this member here. Sometimes there will be other forces that are acting, and then the sum of that will be equal to the normal force, because you remember our forces in one direction must be equal to 0 for our member to be in equilibrium. Now, the good thing about stress, normal stress, is that it can tell us when a member is going to fail, so that we can design for that. So it can help us predict failure. And how does it do that? Now, suppose you have a rod again, and this one is made of mild steel. Now steel has a normal strength of 250 megapascals. Now if we know the dimension of our steel member, let's say you have forces here, force P and force P. Now we want to know how much can we load this member without it failing. Now we know its total strength, and we are going to try and find the stress that is being experienced inside this member. And if the stress being experienced in our member exceeds the strength of our member, then it will fail. For example, let's say we have a rod here, and it has a diameter of 30 millimeters. Now we can calculate the stress so that we can predict the fail. Now let's say our stress is given by normal force over A. Now what we are going to do here is that our strength of our member, we know it, and it is 250 megapascals. We do not know the force that we are applying. We just want to know how much force can we exert on a member before it fails. So we still have our force, and area, we know that the diameter of our rod is 30 millimeters. So it will be pi r squared, which means it's 15 squared. So if we look for our force will be 177 kilonewtons. That means that if you exert a force greater than 177 kilonewtons, then your member will start to fail. Even if maybe you have a column on top of a building. Most universities will have a lot of these columns. Now you will know the strength of the column of your concrete, and if you know the dimensions and you know the strength, then you can look at the stress to check whether the forces that are being exerted on your members are safe enough not to cause failure. If on your member you have forces pulling each side of your member, we call that tension. And if you calculate your normal stress, you will your tension will give you positive stress values. But however, if your member has forces that are pushing against it, your member is experiencing compression. And compression, if you calculate the stress, it will give you negative values. So if you have a member and you calculate the stress and then it gives you a negative value, you will know that the member is experiencing compression. And if you get positive values, you will know that a member is experiencing tensile stresses. Now, this will be important, especially when you are dealing with frames or you are dealing with trusses. It is very important that when you open up your member and you want to deal with the internal forces, you must know whether it is tensile or compression. But it is not always this simple. Sometimes when you have a beam and that beam is curving, you have a moment on that side and you have a moment on that side. Now at the top here, your member will experience compressive forces. So at the top here, where suppose the cross-sectional area of your beam looks like this. So at the top here, you will experience compressive forces because the moments on the sides, when they act at the top here, it will become more compressed. But however, at the bottom it will start to stretch and you will experience tension. So your beam, your area will not only just have compression or tension, it will have them both, one at the top and one at the bottom. Remember that at the top you have compression, and that is basically the idea of normal stress. And in future videos we will discuss shear stress that is acting parallel to the surface of your member and not perpendicular. So for now, let's do some examples to determine normal stress. Now the first one, we have a truss here with three members, member A, B, and C. Now they have pin connections and there's a force here, force P, that is acting to the right. Now it says if the average normal stress in each of the 20 millimeter diameter bars, let's write that down and say the diameter of each bar is 20 millimeters, is not allowed to exceed 150 megapascals. Determine the maximum P that can be applied to joint C. Now it says that the normal stress inside each of this that are 20 millimeters in diameter must not exceed 150 megapascals. Now, how much force can we exert here without experiencing failure in any of the members? Now, the first thing that we're going to do is that we are going to draw the free body diagrams of each of the three joints. So for this joint, I'm going to cut it here. For this joint, I will cut it here. And for this joint, I will cut it nicely here. And let's look at joint C. Now for joint C, you will notice that you have your force P that is acting in this direction. We are at C. You will have your force P that is acting in the positive X axis. And you will also have, if you cut this section here, it will have a normal force inside there. So you will have a force that is CA, that goes down from C to A. Now also you will have a force in this section. When you cut it up, there will be a normal force inside here, and we'll call that force force BC. Now you will notice that the X dimension is 2 meters, the Y dimension is 1.5 meters. So I don't want this 1.5. For ratio purposes, let's multiply them both by 2. So in the X-axis we'll have 3, in the Y-axis we'll have 3, in the X-axis we'll have 4. So the hypotenuse of that will be 5. Now let's draw the forces at joint B. Now at B, so another coordinate system. At B, we have a force. When we cut here, we'll have a normal force acting in here, and we'll call that force C. This one is supposed to be CB, and this one will be BC. Again at B, we'll have, when we cut here, we'll have a normal force acting in there, and we'll call that one force BA. And those are the only forces acting there. You will always also have the reactions. You'll also have the reactions that are being experienced by the joint. But since you do not have any uniaxial forces acting in this axis between A and B, you will not have the X component of the reaction. We'll only have the Y component, and it's acting upwards. We'll call that BY for the reaction of the pin in the Y axis. Now the last one, Y and X. If we look at the forces that are acting at A, you will have a force in here. So at A, you will have a force that goes from AB, and we'll have another force that goes up. When we cut here, there'll be another normal force, and we'll call that force AC. Now there's no axial uniaxial force in the x direction, so we'll only experience the reaction in the y axis. So we'll also have a y reaction at A. Now remember that I'm still looking for the force P. Remember, for equilibrium, the sum of forces in the x direction must be equal to 0. Now we are looking at this joint now. We are saying that all the forces in the x direction must be equal to 0. What are those forces? The first one, it will be the P, and it's acting to the right, so it will be positive. The other one that will be acting in the y direction will be FCB. However, FCB is going diagonal. It just has a component in the y direction. So we are looking for that component. It will be positive FBC. And that component, since it is the x component, it will be given by 4/5. So that will be equal to 0. Now our force P is given by 4/5 FBC. So therefore FBC is equal to 5/4 P. We do not know the force of P, so we'll just keep the variable P there. What I want to do is to calculate all the forces in my members and find which one is the critical one, because this 150 is critical. We want a normal stress that will not exceed this 150 megapascals. So we want a P that is critical. Now I'm going to find all FBC, FAC, and FAB, and then compare how much they are experiencing and see which one is the highest, my critical one. Again, the forces taking up as positive, the forces in y must be equal to 0. Now, which forces are in y here? You have FAC, which is going downwards. So let's call it FCA. I used FAC there. FCA or FAC will be negative because I said it's going down. When, however, up is positive. Now another force that will be acting in the y direction, it will be the component of force BC. The y component of FBC is also going this direction, so it will be negative. Now since it is the y component, we will find it by FBC into 3/5. FBC, we found out that it is 5/4. So we can just say FAC is equal to 0.75 P. Now, what's important here is that you must see that for FBC, I substituted 5/4 P and then made FAC the subject of the formula, and I found out it is 0.75 P. This is 1.25 P. Now we have AC and we have BC. Can we find AB? Now to find AB, I've used up this joint, so let's go to joint B. So at joint B, I take the forces in the x-axis. I say all the forces must give you right is positive, so the sum of forces in x-axis must give you 0. Now, what are the forces in the x-axis at B? You will have a negative FBC at the x component of FBC. So it is negative because it will be going to the left. Now, that means I will have 4/5 since it's the x component, subtracted by FAB. It is all equal to 0. If I substitute FBC again as 5/4, we'll find that FAB is equal to P. Now, I now have FAB that is in here, the normal force in here. I have FAC, which is the normal force in here, and I have FBC, which is the normal force in here. Now, out of these three members, which one is the critical? Now, the one that is critical is the one experiencing the most force. Now, FAB is P, FAC is 0.5 P, and FBC is 1.25. Now, 1.25 P, it will be my critical force because it is larger than the rest. Now that we know our critical force, let's calculate the stress that is acting in that member BC. Now, normal stress is given by force BC over cross-sectional area of the member. We know that the diameter of our member is 20 millimeters, which means our area will be equal to pi 10 squared. Now, we know that our stress is 150 equal to the force in FBC is 1.25 P over the area, which is pi 10 squared. Now we are looking for P. We just have to multiply 150 by pi 10 squared divided by 1.25. Now, if you calculate this, you will find out that your force is equal to 37.7 kilonewton. The last example. Now, with the last example, it says you have a 150 kilogram bucket that is suspended from end E of the frame. Determine the average normal stress in the 6 millimeter diameter wire CF, which is this one, and the 15 millimeter diameter short strut BD. So we're gonna find the normal stress in here and find the normal stress in this wire over here. Now, what do we do first? The first thing that we do is to draw the free body diagram. Now, I'm going to take the free body diagram of the entire structure. You will have of just my members. I will have now a force that is acting here. I will have a force that is acting here that comes from the wire. Now the force will act here coming from the wire, and another one will act here coming from the bucket. Now we know that the bucket weighs 150 kilograms. Now if you want the force, that means we will have to calculate the weight. Now the weight will be 150 kilograms multiplied by 9.8. Now that will give you how much newtons weight is being exerted on the bucket, and then that bucket will be exerting that force through a rope to my member at point E. Now here I have a force CF that I do not know, but I know that it is acting 30 degrees from my horizontal. Now at the bottom here, I have a pin connection. Now with a pin connection, you will have forces reacting in the x-axis and the y-axis. Now these are all my forces that are acting on the larger structure of my member. We still have a strut here, but it is in equilibrium, so it doesn't affect the structure as a system as a whole. So it will still be attached there, but do not have forces that are out of balance. Now another free body diagram will be of the individual members in my board. So the first one will be the horizontal member, CE. Now CE, we have the force of the bucket, which is the weight. We also have a force coming from the strut. We'll now cut the strut here. If we are just focusing on this member, then the strut will now have an effect on the forces that are acting on our member. So that force will be in the direction of that strut, and we'll call that force BD. Now we have CF and BD that they want to find. How about at the corner here? At the corner here, these members are connected to each other. Therefore, we'll have reactions in the y-axis, CY, and the x-axis. Now, let's see if we can find the normal force in the wire CF and our strut BD. Now, using equilibrium again, I will use moment instead of forces as I used here to find my unknowns. I will use the balance of moments. Remember, for the balance of moments, the sum of all moments about a point must be equal to 0 for your member to be in equilibrium. Now at point C, say that anti-clockwise is positive, the sum of moments about C must give me 0. Now what are those moments about C? The first one is that if you take C as your reference, you will have the weight, and that weight will try to cause a rotation in that is clockwise, because that bucket is pulling in this direction. So it will try to cause a rotation in clockwise. So it will be a negative moment. So it will be negative 150 into 9.8, which is the force, times the distance from my my reference point. I know that it is 0.6 plus 0.6, so it will be acting 1.2 meters away. Now, what other moments do I have? Now, this strut here has components in the y direction and the x direction. Now, this component in the y direction will also try to cause a rotation, a clockwise rotation about C. So it will have a negative moment. We do not know FBD, but we can try to find its component. Now, if you look here at our member, the dimensions in the x direction are 0.6 and the dimensions in the y direction is 0.6. That means that the angles here will be 45. So we have 45 degrees. So we can use cos 45 degrees. Even if we use sine, remember that sine 45 and cos 45 are equal, because 45 and 45 are complementary angles. Now they must be equal to 0. Our only unknown in this equation is FBD. So we can calculate FBD, which will give you 4,162 and 03 newtons. Now we know our FBD. Now what we have to do is find the normal stress. Now remember that the normal stress is force over area. So to find this the normal stress in BD, we'll have normal stress in BD will be FBD over the area. Now this strut has a diameter of 15 millimeters, so our area will be pi 15 squared over 4. Now our FBD will be 6,162, and then when you calculate that, you find that the stress there is equal to 23.6 megapascals. Now again, now using this larger free body diagram and looking for moments about A, the sum of moments about A must give me 0. Now what forces causes moments about A? The first one will also be the weight, because if you look at A here, saying that's our axis of rotation, W will be causing the structure to rotate in a clockwise direction. Now if anti-clockwise is positive, then the moment from the bucket will be negative, and we'll have again 150 times 9.8. it is acting at 1.2 meters, 0.6 plus 0.6, so it is acting at 1.2 meters. What other forces? Now another force that we have is CF. Now CF has components in the y direction and the x direction. Now about A, the component that will cause a rotation moment will be the x component of FC. So we know that it's acting at 30 degrees, so it will cause a moment that is anti-clockwise, therefore it will be positive. So FCF sine 30 degrees, the x component of CF, you see it's just the same as drawing it here, and it's opposite to 30 degrees, so we use sine. Now it must all be equal to 0. The only unknown now that I have here is FCF, so FCF will be equal to 1962 newtons. Now the same thing with here. Once I have the normal force in my member, I can calculate the normal stress. Sigma CF is equal to FCF over the area of the Y. This one is of the strut. Now the diameter of the wire is given by 6. It is 6 millimeters. So our area will be pi 6 squared over 4. Now for the FCF, you will enter 1962, and you'll find that our normal stress there is equal to 69.4 megapascals.